I'm Francesco Del Buono, a PhD student at the University of Modena, Reggio Emilia. I am presenting evaluation the integration of datasets. Our paper focuses on the evaluation of a data integration process, which is a task typically performed by domain expert through manual data inspection. This task is particularly heavy in a real business scenario, where the large amount of data makes checking all integrated tuples impossible. Our goal is to address this issue by providing the expert with an unsupervised measure based on word frequencies to evaluate the goodness of a data integration process. But what is data integration? Data integration is the task that aims to integrate many datasets into a unified knowledge representation. The usual pipeline is based on three main steps. First, schema alignment, where dataset information is mapped into a common shared schema. Second, entity resolution, where duplicate entities coming from different data sources are detected. And third, the last step, data fusion, where duplicate entities are merged into a single entry. But how can we evaluate that integration? Typically, data integration in real scenario is usually performed via a tried and error approaches, requiring several iterations where domain experts evaluate the correctness of the integrated dataset produced at each step. For example, a candidate integrated source is created using software application. Then domain experts are required to evaluate its quality and correctness. And then the evaluation leads to modification to the software and the creation of a new improved release of the integrated source, which is subject to further evaluation. Finally, the integration strategy is improved and tuned at each step until the experts are satisfied with the result obtained. As we just introduced, the quality of the integrated source can only be assessed by an expert who must perform this long and economically demanding task of manually inspecting the results of the integration process. Moreover, this process becomes particularly heavy in real business scenario where large amounts of data are available and checking all records is impossible. In addition, new sources may be added over time and the content of the source to integrate may quickly change. This requires executing multiple time the evaluation process. Therefore, an unsupervised measure supporting this task will remove any additional effort by experts and help them in reducing the amount of manual work needed. We introduce an unsupervised procedure based on verification and validation process to check the quality of the integration. First, the verification process aims to check the formal correctness of the integrated dataset by evaluating two concepts: the totality, where each entity of every input dataset should be represented in an integrated dataset, and the minimality, where the integrated dataset should not contain duplicated entities. And finally, the concept of validation, where the validation process checks the correspondency of the informative content of the integrated dataset with the input source. To achieve these two processes, we propose a new idea. In particular, the idea is to provide the expert with an unsupervised measure which quantify how good is an integration process based on the concept of verification and validation. We propose a bidirectional way to see the data integration. First, the more a dataset can be represented by an integrated source, the less there is a loss of information when the integrated source is considered in place of the original one. Second, the more integrated source can be represented by its dataset, and the more it's consistent with them and doesn't contain duplicated data. This measure compares the word frequency distribution of the involved dataset in order to estimate the reciprocal representativeness. This unsupervised technique for evaluating entity integration process proposed in this paper is based on a representativeness function that scores how much a dataset D2 can be represented by a second dataset, D1, through the loss of information in using D1 instead of D2. We implement the representativeness function by analyzing the word frequency distribution in the dataset. And the following definition are the basis of our measure. In particular, we define the word frequency distribution in dataset like, given a dataset D, let V be its vocabulary of terms. The word frequency distribution of the dataset D is a function which map each term W with its frequency in D. Instead, the dataset representativeness score given to dataset D1 and D2, the dataset representativeness L from D1 to D2 quantify the extent to which dataset D1 is represented in D2 by measuring how much the word frequency distribution frequency of D2 approximate frequencies of D1. We propose two representativeness functions to assess the quality of the integration process. In particular, we define input representativeness, how well a source D is represented by the integration E, and output representativeness, the opposite, how well the integration E is represented by a source D. This measure compares the word frequency distribution of the involved dataset in order to estimate the reciprocal representativeness. This representativeness function, in addition, can be used for the verification and validation process. In particular, input-output representativeness score support the verification by measuring the totality and minimality. And moreover, an integration process can be validated by plotting the representativeness score in a two-dimensional Cartesian plane. The x-axis and the y-axis report the input and output representativeness respectively, and value closer to the point 1, 1 to the extreme represent the best performance, and we call the distance from this point representativeness distance, and we claim that this is a measure of the validation of an integration approach. Indeed, the more we depart from the best score, and the more the correspondence between entities in the input integrated dataset decrease. The experiment evaluation of the effectiveness is carried out on 12 publicly available use cases from the benchmark of the Magellan tool. That is the main reference to evaluate entity matching approach. Each use case consists of two datasets of entity, and the ground truth contain pair of entity, one for each dataset, and labeled as matching and no matching item. Other experiments have been presented in the paper demonstrating the effectiveness and the performance of the approach. In particular, we evaluate to which extent the representativeness supports the verification and the validation of an integration process. Then we compare alternative representative measures on the basis of they react to possible error in the integration. And finally, an evaluation of controlled integration scenarios is analyzed. Now, I'm showing only 3 experiments among the one presented in the paper. In the first experiment, we evaluate the extent to which representativeness supports the verification and validation of an integration process. Input representativeness for the totality, output representativeness for the minimality, and representativeness distance for the validation. The idea of the experiment is to modify the dataset in a controlled way and to check if the representativeness measure vary as expected to reflect the changes. The first plot on the left shows how the input representativeness score measures the totality of integration process. In particular, for each step, a number of integrated datasets have been created from the ground truth by selecting an increasing percentage of ground truth entities as specified in the x-axis. The input representativeness score computed with this reduced dataset is shown on the y-axis, and as you can see, low input representativeness score corresponds to integrated dataset composed of a reduced number of entities. In a similar way, the second plot shows on the x-axis the percentage of duplicate entities that we have introduced in a perfect integrated dataset, and on the y-axis the corresponding output representativeness score. As expected, the higher the number of duplicate and the lower the value of the output representativeness. This is due to the existence of entities in the input dataset that don't have any correspondency in the integration. Finally, the sort plot evaluates how well the representativeness distance measures the validation of integration approach. We alter the dataset by removing and by duplicating the same percentage of entity. And x-axis represent this variation. Instead, the y-axis shows the corresponding value of the representativeness distance. As expected, the distance grows with the increase of duplicated and missing entities, providing an overall validation of the process. We need to note that the slope of the curves is less sharp than the previous ones. This is due to the joint contribution of the input and output representativeness in the definition of this measure. Next, we perform an evaluation of alternative techniques because we propose actually a specific way of computing representativeness based only on word frequency distribution that could have some limitation. We need to consider alternative for computing this input representativeness. In particular, we consider the Jacquard-based similarity, the BLEU score, and free embedding technique that capture syntactic and or semantic similarity that are word-to-back, fast text, and GLOW. We compute the similarity using this function between the input data source and integrated entities, where for each input entity we consider the maximum value computed, then the mean of all maximum value is the input representativeness measure for the considered input data source. We compare this alternative representativeness on the basis of how they react to possible errors in the integration process. We define a unique entities, these entities in the input dataset, which are not merged with other entities in the integration process. And we evaluate the impact of merge errors on the input representativeness by merging unique entities with other entities in a wrong way. We created variation of the use case dataset where different percentage of error have been introduced in the ground truth, as specified in the x-axis, and we measure the difference of the input representativeness score measured with respect to the ground truth that is shown on the y-axis. The input representativeness, independently from the approach used for its computation, decrease when the error increase in all use cases and with all the approaches. However, we observe that our measure better represents this mistake by showing the largest variation. Finally, in the last evaluation scenario, we simulate for each use case 3 common integration scenarios between dataset describing the same entities, dataset describing different entities, and dataset describing common entities. In particular, a table on the right shows this result, and the column that we can see are EM and EC, that are the integrated dataset obtained by matching and concatenating all the entities respectively. Instead, EP represents the perfect integration by matching only the correct record in the third scenario. Therefore, the best integration, we expect that are EM to be the best in scenario 1, EC in scenario 2, EP in scenario 3. The both value indicate the best one for each dataset in each scenario. And the measure perform, how can we see, correctly in almost all evaluation. And how can we see this demonstrate that representativeness score offer an explanation of why an integration strategy can be preferred to another one. In conclusion, we propose an unsupervised measure to evaluate the quality of the integration process by analyzing the word frequency distribution of the data involved. The experimental evaluation showed that the representativeness can provide a tool for verifying and validating an integration process, and future work will focus on the unsupervised evaluation of the entity matching task. Thank you very much for the attention.